There are mainly we can classify the optimization algorithms into, like, there are three categories. The zeroth order optimization, where there is no derivative, but it has its own challenges. The scaling itself becomes very difficult in zeroth order optimization. We have covered this part in detail, so I will not go into in deep of it, but I will explain some other things. Then we have also looked at the first order optimization algorithm, where we look at the gradient descent, where we assume that there is a error function. We hypothesize that this is the error function that I want to use to optimize my model. Now that error function has its own error surface. So basically, error function will generate some numbers. Those numbers, if you plot, it will create some kind of graph. That graph is our surface. So because we have the multidimensional cases most of the times in machine learning, so that's why it's surface. That surface, when we do the gradient descent, our objective, because it's an error function, we have to reduce the error. So we say that it's a minimization problem. If instead of error function, if it is a, let's say, the reward function, then we will increase the reward, and we will say that this is a maximization problem. So most often the terminology and the setup that we use in machine learning is minimization problem, because we use some error function that we have to minimize. Now, in the first order optimization, we go for the first order derivative. First order derivative tells us at any point on the surface, if I take a derivative, it will tell me what is the slope of that. At that particular point where we are taking the derivative, it draws a line. The slope of that line is the outcome of that first order derivative. So that if the slope of that is negative, that means we are going downhill. If the slope is positive, that means we are going uphill. When we are going uphill, that is not the desired situation, because we have to go for minimization. Uphill is a desired situation when we have the maximization problem. So for the minimization, we go for the downhill. So anytime when we get the uphill gradient, we do take the minus of it and then take the step in the direction of the gradient, next step in the direction of the gradient. Now, most of the first order derivative based optimization algorithms, where they differ, how do you choose the next step? That is the main difference in many of these first order optimization algorithms. So do you choose the next step at a fixed, like every next step is going to be a fixed step, or it is going to be based on how many steps previously you have taken? So that means the first step and the second step and the third step, they are all decreasing in size. Third is that whether the second step and third step, are they taking the first two into consideration or not? So that is how much back we are looking at before taking the next step. So this is a very similar situation. For example, if you are going through some unknown place and you have to choose some certain direction, then probably you look left, right, back, and you try to identify what is your position. Are you in the right spot or not? And then on the basis of that, then you choose your next step, in which direction you have to go. Then after going to the next stage of your navigation in that unknown environment, you will again look for what looks like the most probable way of going forward. You will try to look for some signs. You will try to look for whether it's a familiar environment, or is there somebody I can ask and then go in that direction. So all that kind of thing. So similarly, whatever the variation that we see in real life, similar to that, you can create analogies in. And as far as I have deliberated on these aspects, I find that real life analogies are perfect match for many of the machine learning settings. All right. So in first order derivative, as I mentioned, you can have fixed step size. We also call that as a learning rate. At what rate you are learning, basically. So multiply step size multiplied by the learning rate. You can have a reducing step size. You can have a adaptive based on the previous step size. If the previous was very large step, then probably you need a smaller step at this stage. Otherwise, the minima will be oscillating on the surface. So sometimes it will go on the right side, sometimes it will go on the left side, but it will not reach to the minima point. So like jumping over the minima left and right. So you need to take smaller step if you have earlier taken the bigger step. So these are the different variation. On basis of this, many optimization algorithms are created in the first order case. Then also there is a variation depending on how many data points you use together to make the decision. For every data point every sample or example that you are getting, are you using that as a criteria, or you are accumulating the number of examples and then deciding which direction to go? So these are different variations. All right. There are tens of such algorithms. Now then the third classification of optimization algorithm is the second order optimization algorithm, where we use the Newton's algorithm, where we compute the gradient of the gradient. Why I am saying gradient? Because that point is a multidimensional. It's not a scalar point where if I take the derivative, it becomes a derivative. If it's a vector input, basically. It's a multidimensional in the sense it's a vector input. Therefore, when we take the derivative of a vector, we say it's gradient. If I'm taking one more time gradient, we say it's a gradient of gradient, which is nothing but a second order derivative. Second order derivative, first order has already given me the direction. Second order tells me that what is the curvature, how the shape of that particular position is. It tells me about that shape. So there are many algorithms that are derived from the Newton's algorithm. On the basis of that, many second order algorithms are also created. When we talk about second order algorithm, what basically we are doing at each step, we are computing the gradient of the gradient, and if you put all the gradient of the gradient at different steps in different dimensions, so you have to choose the next step. How do you choose the next step? Evaluate in the surrounding area, all the other steps, and then choose whichever is the giving you going towards minima. So when you compute the gradient of the gradient at multiple points before taking the next step, and you arrange those in a matrix, it becomes your Hessian. Okay, so Hessian is nothing but the matrix of gradient. Every item in that matrix is the gradient of a gradient. So for example, x with respect to x1 with respect to x1. So derivative of x1 with respect to x1, we are taking one more time derivative. Then x1 with respect to x2. So derivative of derivative in these two dimensions. Then x1 with respect to x3. So different dimensions are there. For each dimension with respect to another dimension, you are taking gradient of a gradient. And when you arrange this into a matrix, it becomes Hessian. Now, computation of Hessian itself is a time-consuming task, and it's a memory-intensive task because you have n square entries. If n features are there and dimensions are there in your data set, then there are n square entries. Computing those n square entries and then taking the decision on the basis of it's a very costly affair for every iteration that you take in each of the epochs. So therefore, there are some approximation. So instead of computing the whole of the Hessian, so now we are getting into the variations, and these variations create different optimization algorithm in the second order. So should we take the diagonal as the criteria and forget about the rest of the entries in the Hessian matrix? That is one criteria. Should we approximate instead of computing the whole? Should we approximate only limited entries in the Hessian? That's another criteria. So basis of that, many second order optimization algorithms are also created. Not all of these algorithms have proven useful in all settings. Some algorithms work in certain settings, another set of algorithms work in another set of settings. But by and large, Adams and stochastic gradient descent, SGD. If you talk about TensorFlow terminology, there is a optimizer called SGD. So these are the two very popular. Then RMS prop is also popular. If you have the multi-class classification, for example, softmax is the last layer of your network, then you go for the Adam or SGD based.